They had no internet, no global shipping routes, no phone calls between continents. A civilization in Peru and a civilization in Ireland could not have sat down together and compared blueprints. And yet, when you put their buildings side by side, when you line up their drainage pipes, their acoustic chambers, their solar alignments, their self-healing mortar, the rules are the same, identical in principle, matched in execution, thousands of miles apart. This is not a coincidence theory. This is a pattern carved into stone and proven by MIT researchers, Stanford University acousticians, and materials chemists who published their findings and had to sit down afterward, because what they found was genuinely hard to explain. These are the silent engineering rules shared by distant ancient civilizations. The rules nobody told them to follow, the ones they discovered themselves, and somehow all agreed on. If you value documented archaeological and engineering history like this, subscribe. It is the best way to support our work. Also, drop a comment telling us which city you're watching from. This script is fully researched and factual, drawing primarily from two sources that go deep into the evidence. The peer-reviewed journal Science Advances, which published the MIT and Harvard study on Roman concrete in January 2023, authored by Admir Masix and Linda Seymour and their team. Real materials, science, not pop history. And from the Stanford University Center for Computer Research in Music and Acoustics, which has been running archaeoacoustic fieldwork at Chavin de Huántar in Peru since 2007 under principal investigator Miriam Kohler, backed by grant-funded on-site experiments with actual participants. Now back to the information. The first rule, sound is a building material. You do not get to that conclusion easily. You get there through failure. You build a chamber. You stand inside it. You notice something happens. You build another chamber, shaped differently. Something else happens. You keep going until the chamber does exactly what you wanted. That process takes generations. It requires that someone remember what the previous generation learned. It requires that the knowledge be treated as worth preserving. It requires a civilization that understands, without the vocabulary of physics, that the material properties of air inside a shaped stone space are as real and controllable as the material properties of the stone itself. 3,000 years ago in Peru, they had that understanding. 2,000 years before that in Ireland, they had it too. Nobody told them about the other one. In 2007, a team from Stanford University packed acoustic measurement equipment and flew to the Peruvian highlands to a place called Chavin de Huántar, a ceremonial center 3,000 years old sitting at 10,000 feet above sea level in the north-central Sierra. Chavin predates the Inca by more than 2,000 years. The civilization that built it left no decipherable written language. What it did leave was a labyrinth. The interior of Chavin de Huántar is a network of stone-walled underground galleries. Narrow corridors, rectangular alcoves, hidden chambers, carved so precisely that the Stanford team could take acoustic measurements that revealed what the builders already knew. Sound behaves differently in every section of the gallery. The walls filter certain frequencies. They amplify others. And the specific frequency that gets amplified, the one that the gallery architecture seems almost surgically designed to favor, is the exact frequency produced by a specific instrument excavated from the site itself. In 2001, Stanford archaeologist John Rick and his team unearthed 19 intact Strombus gelatus shells at Chavin, giant marine conch horns, known in the Andes as pututus, pulled from 3,000 feet above the ocean they once inhabited. These are not random artifacts. They are use-worn. They have been played. And when Miriam Kohler and her team tested the acoustic frequency of those pututus against the measured resonance of the Lanzon Gallery, the inner chamber housing Chavin's central stone deity, they found a match. The architecture and the instrument were tuned to each other. A central duct was built to connect the Lanzon chamber to the open-air circular plaza. That duct is an acoustic filter. Sound from inside travels through it, gets shaped by it, and arrives at the plaza changed, directionless, sourceless, seemingly coming from everywhere. The oracle at Chavin did not speak from a body. It spoke from the walls. Now leave Peru, travel north and east across an ocean, cross Britain, and keep going until you hit northeastern Ireland in 3200 BC. You are standing in front of Newgrange, a massive passage tomb, a rounded mound of earth and stone 60 meters wide, 13 meters tall, older than Stonehenge, older than the Egyptian pyramids, older than writing itself. Inside is a stone passage, 19 meters long, leading to a cruciform chamber at the center. Once a year at the winter solstice, for exactly 17 minutes, a single beam of sunlight shoots through a purpose-built roof box above the entrance and travels the full length of that passage to illuminate the back stone of the central chamber. The roof box is a piece of precision engineering, not a hole or a crack. It is a designed aperture, exactly sized, exactly angled, constructed by Neolithic farmers who had calculated the sun's position at sunrise on the shortest day of the year and built the entire mound around that calculation. In 1994, a consortium from Princeton University conducted acoustic measurements at megalithic chambers across Britain and Ireland, including Newgrange and Wayland's Smithy in England. What they found was a sustained resonance, a standing wave, in a frequency range between 90 Hz and 120 Hz. That is not an accident. Those dimensions do not produce that resonance range randomly. The chambers were built to that frequency. 90 to 120 Hz is, for reference, the low range of a human male voice. It is also, as psychoacousticians have documented, a frequency range that, when sustained in an enclosed space, alters human perception. People in those chambers, during ceremonies, during firelit rituals, would have experienced something they could not explain mechanically. The architecture was producing it on purpose. Peru, Ireland, 3200 BC and 1000 BC. No contact. Same rule, build the sound into the structure. The same pattern appears at the Hal Saflieni Hypogum in Malta, a subterranean ritual site carved entirely from rock dating to 3600 BC. Its oracle room produces standing resonances between 100 and 110 Hz. The builders of Chavin in Peru and the builders of the Maltese Hypogum were separated by 10,000 kilometers and at least 1,500 years. The physics they were applying is identical. The second rule, water management is the actual city. Mohenjo-Daro sits in what is now Pakistan's Sindh province, on the right bank of the Indus River. It was constructed around 2500 BC, during the mature Harappan period of the Indus Valley civilization. You have almost certainly never heard it described with the specifics it deserves. Mohenjo-Daro covered nearly 500 acres. It had more than 700 wells, not communal wells shared by whole neighborhoods, but individual household wells, meaning the average home had its own water source. Every single house in the city, every modest structure, was connected to a covered sewer network running beneath its grid-patterned streets. The main drainage channels were 2 feet deep and 3 feet wide, lined with waterproof brick. Drains from upper-story bathrooms ran through enclosed terracotta pipes that emptied into those street channels. The channels had inspection holes at regular intervals. They cleaned those systems. They maintained them. And here is the fact that makes historians slow down and reread the sentence. European cities did not achieve this level of sanitation until the 19th century AD. Mohenjo-Daro had running waste removal in 2500 BC. The Great Bath at Mohenjo-Daro measured 39 feet long by 23 feet wide and 8 feet deep. Its floor and walls were waterproofed using a layer of bitumen, tar, sandwiched between 2 layers of brick. It required approximately 21,600 gallons of water at capacity. Water came from a large well next to it and drained through a complex outlet system. This is not bathing infrastructure, this is hydraulic engineering. Now go to Rome, 600 years before the Common Era, 3,000 kilometers northwest of Mohenjo-Daro, in a civilization the Indus Valley people never met. Rome built the Cloaca Maxima, one of the world's earliest sewage systems, beginning construction in the 6th century BC. It drained the marsh between the Palatine and Capitoline hills, stone-lined, arched, large enough for a boat to pass through sections of it. By the time of the Roman Empire, every major city in the empire had a version of the same system. Covered drains, inspection points, gravity-fed flow, connection from private homes to public mains. The Vitruvian manuals, the 10 books on architecture written around 25 BC, specified exactly how water should enter and exit urban structures, with ratios and grades and specific language about the slope required to prevent stagnation. The Minoan civilization on Crete deserves more space than history gives it. From around 3200 BC, Minoan palace complexes at Knossos and elsewhere were built with drainage systems using clay pipes. And here's the technical detail that historians have been arguing about for decades. Those pipes were conical. One end was wider, one end was narrower. The narrow end fitted into the wider end of the next pipe section, creating a sealed joint. Wastewater and stormwater moved through these joints without leaking. The Minoans were running stormwater and sewage simultaneously through separate pipe networks in some palace complexes. They also built cisterns and aqueducts. Researchers at the International Journal of Sustainable Environmental Technology, reviewing the historical development of sewage systems worldwide, noted that the Minoan and Harappan civilizations were the first in human history to operate well-organized and operated sewerage and drainage systems independently after around 3000 BC in Crete and in the Indus Valley, respectively. The Indus Valley and Roman civilizations were not in contact when they developed these systems. No trade route connected Mohenjo-Daro to pre-Republic Rome. Researchers at the journal Hydrology and Earth System Sciences, in a 2020 paper from P.K. Singh and colleagues, documented explicitly that the Indus Valley's water management was so comprehensive that, quote, no other city in the ancient world had developed such a sophisticated water and waste management system. Even during the Roman Empire, and some 2,000 years later, these kinds of facilities were limited. They arrived at the same answer through completely independent problem solving. The rule was not shared. The rule was discovered. And they were not the only ones. The Minoan civilization on Crete from around 3000 BC built drainage systems in their palace complexes using clay pipes with conical fittings, tapered at one end to slide into the next pipe, identical to a technique independently used in Mohenjo-Daro. The Minoans and the Indus Valley people had some indirect contact via trade networks, but the clay pipe fittings appear in both archaeological records without clear evidence of transfer. Both societies reached the same engineering solution for moving water through enclosed conduits. The third rule: build for the earthquake you have not felt yet. The Inca city of Cusco sits at 11,152 feet above sea level in the Peruvian Andes, one of the most seismically active zones on Earth. The Inca built their finest structures there using what engineers now call polygonal ashlar masonry, irregular stone blocks cut to fit against each other without mortar, with contact surfaces that touched at multiple angles simultaneously. Modern computer modeling of these walls shows that the irregular shapes optimize load distribution better than regular rectangular blocks. During a seismic event, the joints flex, the stones move, then they resettle. The wall survives. Walls also leaned slightly inward with rounded corners, adding passive stability without any additional fastening mechanism. The system required no glue, no metal, no chemical bond. It required only geometry, patience, and an understanding of force distribution that took generations to develop. The largest stones at Sacsayhuaman, the massive Inca fortress above Cusco, are estimated at 100 to 200 tons, as documented in a 2023 analysis by Charavanja and colleagues published in engineering literature. Moving these stones up a mountain without wheels and without horses or oxen, which the Inca never used for hauling, required a logistical system of organized human labor operating on a scale that modern project managers still study. And yet the stones arrived, and yet they fit. The gaps between blocks at Sacsayhuaman are, in many cases, less than half a millimeter. This was not done quickly. This was a civilization that decided precision was worth the time it cost, because a stone that fits perfectly is a stone that does not need to be replaced. Water engineer Ken Wright, who studied Inca structures for decades, documented that 60% of Inca construction effort at any given site was underground, hidden. The above-ground stone walls are what tourists photograph, but the real engineering was in the foundations, deep into bedrock wherever possible, with drainage systems planned from the initial survey. At Machu Picchu alone, researchers have identified over 130 drainage holes built into the structure during initial construction. Not added later, not retrofitted, planned from day one. Water accumulation was the enemy. They knew that from the start. A powerful earthquake struck Cusco in 1650. Spanish colonial buildings, stone structures built by a civilization that had been constructing churches for over 1,000 years in earthquake-prone Mediterranean regions, collapsed across the city. The curved Inca retaining wall of the Coricancha, the sacred Inca ceremonial complex, was unscathed. The Spanish rebuilt their church of Santo Domingo anchored to that Inca wall. In 1950, another major earthquake hit Cusco. More than half the buildings in the city collapsed again. The church of Santo Domingo collapsed again. The Inca curved wall stood again. That wall has now survived 2 catastrophic earthquakes that leveled everything around it, built without mortar in the mid-15th century by a civilization that never invented the wheel, now moved to China's Shaanxi province. The Yingxian wooden pagoda, built in 1056 AD along a documented seismic belt in northern China, used a joining system called dugong, interlocking wooden brackets that transfer load from roof beams to columns without nails or glue. Now, the brackets stack in a series, each layer mortising into the next. Under seismic loading, the dugong joints flex, absorb energy, and release it. The pagoda has survived multiple earthquakes over nearly 1,000 years. The architects who designed Yingxian had no contact with the Inca masons building Cusco's polygonal walls 4 centuries later. Neither had contact with the builders of the Nabatean temple at Palmyra in Syria, who used lead-enclosed metal dowels in their stone connections, specifically to provide seismic flexibility, a technique documented by archaeologists studying what are now ruins in eastern Syria, dating to around the 2nd century AD. Independent civilizations, same diagnosis. The earth moves, designed for movement. Researchers published in a 2022 paper in the journal EOS, analyzing archaeoseismological evidence at Cusco, cataloged thousands of displaced blocks and fractures in Inca stonework that recorded the ground-shaking direction of at least 2 major earthquakes, one of which had been entirely undocumented in historical records. The Inca walls remembered the earthquake and the geometry of how they bent. Carlos Benavente and his team at the study's core noted that the results could help update Peru's building regulations, which currently underestimate inland fault hazards. The ancient engineers had already mapped those faults with their own bodies. The 4th rule: make concrete that heals itself. In January 2023, a team from MIT, Harvard University, and laboratories in Italy and Switzerland published a paper in Science Advances, the peer-reviewed journal of the American Association for the Advancement of Science. The lead author was Admir Masick, professor of civil and environmental engineering at MIT. The paper solved a riddle that had been open for decades. Why does Roman concrete last 2,000 years when modern Portland cement begins degrading after 50 to 100 years? The answer was in the lime. Roman concrete was made by combining volcanic ash, called pozzolana, named for the deposits near Pozzuoli on the Bay of Naples, with quicklime and water. For years, when researchers examined samples of Roman concrete, they found small white chunks of lime scattered through the mix and assumed these were evidence of poor mixing technique. Sloppy workmanship. Masick's team looked closer using high-resolution multi-scale imaging and chemical mapping. The lime clasts were not a flaw. They were the entire mechanism. The Romans mixed their concrete using a process the researchers called hot mixing, combining quicklime directly with the pozzolana and water at extremely high temperatures, producing an exothermic reaction that distributed reactive lime particles throughout the material in a specific crystalline form. When a crack formed in the finished concrete and water seeped in, the water dissolved the edge of a lime clast, generating calcium ions that reacted with the volcanic ash to grow new calcium carbonate crystals inside the crack. The concrete sealed itself, from within, without human intervention. The researchers confirmed the mechanism experimentally. They created cracked samples of Roman recipe concrete, and within 2 weeks, those cracks had healed. The control concrete, modern Portland cement, remained cracked. The Pantheon in Rome, dedicated in 128 AD under Emperor Hadrian, has the largest unreinforced concrete dome in the world, 142 feet in diameter. It is intact. The harbor structures at Caesarea Maritima in Israel, built using 35,000 cubic meters of pozzolana, concrete poured underwater in the Mediterranean, beginning around 15 BC, are intact. The concrete has not just survived. In marine structures, seawater percolating through the pores reacted with the volcanic materials to grow aluminum tobermorite crystals, a rare mineral that reinforces the matrix. The harbor got harder as centuries passed. Modern concrete exposed to seawater deteriorates within decades. Roman harbor concrete, 2,000 years old, is still doing chemistry. Now travel to Copan in western Honduras, where Maya masons built lime plaster sculptures and temple facades beginning around 400 AD. Copan's intricate lime sculpture and temple plaster has remained structurally intact after more than 1,000 years of exposure to hot, humid conditions that eat modern cement. A study highlighted by the Times of Israel in October 2023, drawing on research by Carlos Rodriguez Navarro at Spain's University of Granada and Admir Masick's MIT group, found that Maya builders in the humid Copan region developed lime mortars with specific additives, plant-based organic compounds from local species, that gave the plaster different properties than standard lime. The organic additions improved carbonation and reduced porosity. The result is a material adapted to its specific climate. In southern India, researchers studying the Vadakamnathan temple in Thrissur, Kerala, an active Hindu temple with elements dating back several centuries, found that the lime mortar binding its structural elements contained herbal admixtures, including kadukai, the fruit of Terminalia chibula, and palm jaggery, an unrefined sugar from the Borassus palm. A 2022 study in the journal Environmental Science and Pollution Research confirmed that these organic additives increased compressive strength and reduced porosity in the mortar matrix. Thirumalini Selvaraj, a civil engineering professor at India's Vellore Institute of Technology, and colleagues found that temples in India's humid coastal zones used jaggery additions to protect against salt damage, while earthquake-prone highland regions used rice husk to create lightweight floating bricks with different structural dynamics. The locations are thousands of kilometers apart. The builders never exchanged a word, but the rule they landed on was the same. Lime mortar alone is insufficient. Modify it with local chemistry to meet local conditions. Roman engineers solved this by importing volcanic ash from Pozzuoli across their entire empire. Records show that at Caesarea Maritima alone, at least 52,000 tons of pozzolana was shipped from the Bay of Naples to the coast of Israel, the equivalent of 100 to 150 large cargo vessels. Indian temple builders solved the same problem with jaggery and Terminalia chebula. Mayan builders at Copan solved it with indigenous plant extracts. Nobody shared the answer. Everybody arrived at the same category of answer. Chemistry first, stone second. The fifth rule: align the building with the sky and use the sky as a clock. Around 3000 BC, at the same moment that the people of Newgrange in Ireland were engineering their solstice chamber, other builders on Egypt's Saqqara Plateau were arranging the great step pyramid complex for the pharaoh Djoser, the oldest important stone building in Egypt, 4,700 years old, designed by the architect Imhotep, who was later deified. The Great Pyramid of Giza, built around 2560 BC under Khufu of Egypt's 4th dynasty, has its 4 sides aligned with the cardinal directions, north, south, east, west, to better than 4 arc minutes of accuracy, which is 1/15 of a degree. This is more precise than many modern constructions achieve. Archaeoastronomers studying Egyptian pyramid orientation, published in research by Chaltut and Belmonte, reviewed in multiple papers in the Journal for the History of Astronomy, documented that the temple of Amun-Re at Karnak was specifically aligned to the winter solstice sunrise and summer solstice sunset, the same event happening from the opposite direction in the same calendar. Nabta Playa in southern Egypt, an archaeological site in the western desert, contains what researchers at the University of Colorado documented in March 1998 as possibly the world's earliest known archaeoastronomical device, dating to the 5th millennium BC, predating Stonehenge by over 2,000 years. The site includes alignments of stones in a calendar circle that indicates the approximate direction of summer solstice sunrise. The people who built Nabta Playa were nomadic cattle herders. They were not a settled civilization in the conventional sense. They had no permanent cities. And they still built a solar calendar from stone in the desert because knowing when the rains were coming was the difference between life and starvation. The sky was the most important engineering problem they had. The Chanquillo Observatory in Peru's Casma Sechin region dates to around 200 to 300 BC. It consists of a line of 13 towers spread across a hilltop ridge, positioned such that a viewer standing at specific observation points on the east or west could watch the sunrise or sunset mark different points along the tower sequence over the course of the year, creating a solar calendar accurate to within 1 or 2 days across the entire annual cycle. The Casma Sechin culture that built it is not the Inca. It is not Chavin. It is a separate Peruvian culture, predating the Inca by over 1,500 years, that independently constructed a working solar observatory using architecture as the instrument. 3 different pre-Columbian Peruvian civilizations: the Casma Sechin culture at Chanquillo, the Chavin culture in the highlands, and the Inca at Machu Picchu and Cusco, all built solar engineering into their sacred spaces. None of them learned it from the others. They all looked up and saw the same problem. On the Salisbury Plain in England, construction on Stonehenge began around 3000 BC and continued in phases for roughly 1,500 years. The site is aligned both to solstice events and to lunar standstills, the 18.6-year cycle of the moon's maximum and minimum rising and setting positions. Gerald Hawkins published this analysis in 1965 in his work Stonehenge Decoded. More recent archaeoastronomical survey presented at the New England Antiquities Research Association Conference in April 2024 by Mark Carlotto and published December 2024 on the Before Atlantis research platform, updated a worldwide survey of more than 200 ancient sites and found that approximately 40% showed clear alignments to solar, lunar, or stellar events, far beyond statistical chance across the sample. Chichen Itza, the Maya city in Mexico's Yucatan Peninsula, was built between approximately 600 AD and 1200 AD. The Central Pyramid, El Castillo, 30 meters tall, 9 stories, staircases on all 4 faces, is aligned such that on the spring and autumn equinoxes, the shadow of the staircase edge falls across the pyramid's northern face in a series of triangular shapes that produce the visual illusion of a serpent moving down the steps toward the stone snake head at the base. This is not accident. Each stair is cut at a precise, measured angle. The total number of steps, 365, 1 for each day of the solar year, confirms the astronomical intent. The caracol at Chichen Itza, a circular tower, has its doorways and windows aligned to the path of Venus across the sky. Angkor Wat in Cambodia, the largest religious monument on Earth, was built by the Khmer Empire beginning in the early 12th century AD under King Suryavarman II. Its main entrance faces west, the only major Khmer temple oriented westward, which aligns it with the setting sun, associated in Hindu tradition with Vishnu, the deity to whom the temple is dedicated. During the equinoxes, the sun rises directly over the central tower when observed from the main entrance causeway. Researchers using Google Earth data and the astronomical software Stellarium in a systematic archaeoastronomical study reviewed in the Journal of the Siam Society confirmed that Angkor Wat's cardinal alignment and the anomalous orientations of 2 peripheral Cambodian temples were each explicable through specific astronomical and symbolic logic, not terrain constraints. These builders did not talk to each other across oceans, but they were all watching the same sky, and they all reached the same conclusion. The building should be part of the sky's movement. The sun is the clock. The monument is the clock face. Stone is the hand. The 6th rule: build underground first. We have already seen this with the Inca, who put 60% of their construction labor below ground. The rule was not theirs alone. The step pyramid at Saqqara, built under the direction of Imhotep around 2650 BC, was surrounded by a hydraulic engineering system that a 2024 study published in the peer-reviewed journal PLOS One, led by Xavier Landreau of the Paleotechnic Research Institute in Paris, proposed to be among the most sophisticated of the ancient world. Landreau and his team, drawing on a review of multiple research programs and original landscape survey of the Saqqara Plateau, identified the Gisr el-Mudir, a massive stone enclosure previously assumed to be purely symbolic or defensive in function as a dam designed to capture seasonal floodwater. 2 vertical shafts inside the pyramid complex, connected by a 656-foot underground gallery they proposed, enabled a hydraulic lifting platform. Blocks placed on a float inside a flooded shaft could be elevated by water pressure, then slid horizontally onto the pyramid's rising levels. The study was published August 6, 2024, and immediately attracted serious debate from Egyptologists who noted the absence of explicit textual documentation. But the underground infrastructure is there. The shafts are real. The gallery is real. The Gisr el-Mudir is real and massive. What is not debated is that the underground infrastructure of great ancient structures was always more sophisticated than the visible portion suggests. At Mohenjo-Daro, the urban platforms on which the city was built were raised 20 feet above the floodplain, and their internal structure included drainage to prevent pooling during heavy rain, invisible engineering that made the visible city possible. At Shavin Dewantar, the labyrinthine galleries that generate the acoustic effects are the foundation. At Newgrange, the chamber that catches 17 minutes of winter solstice light is inside a mound of earth that is 60 meters wide and 13 meters tall. The visible mound is the container for invisible precision. The Roman Pantheon's dome, made of lightweight pumice aggregate at its crown and heavier volcanic rock at its base, a deliberate gradient of density, sits on walls so thick they function as structural masses, not simply vertical supports. The walls are 8.2 meters thick. You cannot see that from outside. In every case, the thing you see is the last layer built. The engineering is underneath it. If you are still watching, subscribe and tell us your city in the comments. This channel does not make things up and does not cut corners on research. The sources you just heard are the peer-reviewed journal Science Advances, January 2023. The MIT and Harvard study on Roman concrete by Massis and Seymour, the Stanford University Center for Computer Research in Music and Acoustics, whose Shavin Dewantar Archaeological Acoustics project fieldwork from 2007 through the present is documented on their public research pages and in the journal Time and Mind, Volume 10, Number 1, and the PLOS. One study on the Saqqara hydraulic system by Landro and colleagues, published August 2024. These are not television documentaries. They are controlled, peer-reviewed, published science. Now back to the story. There is one more thing. Across every example above, there is a pattern inside the pattern. None of these solutions were simple. None of them were the first idea anyone had. The Inca polygonal ashlar walls were used only for the highest status buildings, temples, fortresses, palaces, because the process of fitting irregular stones required repeated lifting, adjusting, and repositioning, with abrasion and percussion work measured in fractions of millimeters. Archaeologist Jean-Pierre Protzen demonstrated through stoneworking experiments that Inca tools, bronze chisels, stone hammers, wooden wedges, could achieve those tolerances, but it required time and skill so extraordinary that simpler mortar-based construction was used everywhere it could be. The fine masonry was expensive. It was chosen precisely because it was expensive, because only a civilization confident enough in its engineering to spend that kind of labor on a single joint was going to build a wall that survived a 200-year earthquake sequence. Roman engineers specified their pozzolana ratios in writing. Vitruvius, around 25 BC, wrote in his 10 books on architecture that the ratio for structural mortars was 1 part lime to 3 parts pozzolana and 1 to 2 for underwater work. The recipe was documented and transferred as professional knowledge across the empire. And still, when that knowledge was lost, when the Western Roman Empire collapsed in 476 AD and the specific pozzolana supply chains from Pozzuoli to provincial construction sites broke down, nobody in Europe replicated Roman concrete for more than 1,000 years. The formula was in books. The books survived, builders could read the books, and for over a millennium they could not make it work without the volcanic ash from the Bay of Naples. The chemistry was the secret. Not the writing about the chemistry. The people who built the acoustic galleries at Shavin Dewantar 3,000 years ago in the Peruvian highlands did not write any of this down. Their language is undeciphered. What they left was the gallery itself. Stanford University brought acoustic measuring equipment to that gallery in 2008 and spent years confirming what the builders had already confirmed when they cut the stone. When Miriam Kohler and her team conducted psychoacoustic experiments using volunteer participants from the archaeological research program, testing auditory localization inside those gallery spaces with sounds produced by replicas of the site's own pututus, they found that listeners in specific gallery positions could not accurately determine where a sound was coming from. The gallery's architecture had created deliberate directional ambiguity. The oracle could be anywhere. The voice could be nowhere, or everywhere. And the builders knew that when they set the first stone. This is the thing that makes every engineer who studies these sites eventually fall quiet. These were not people who got lucky. These were not people who stumbled into acoustic physics or hydraulic mechanics or seismic engineering. They were watching, over generations. They were testing. They were failing and rebuilding. The Saqqara Plateau shows at least 3 different structural phases before the step pyramid reached its final form. Imhotep's design was revised and expanded during Djoser's reign, with layers of accumulated engineering decision-making visible in the stages of construction. Stonehenge was built in phases across 1,500 years, meaning each generation added to the calculation of the previous one. Newgrange's builders positioned the roof box aperture at an angle of less than 1 degree, off the precise azimuth of the winter solstice sunrise, at 53 degrees north latitude in 3200 BC, using sightlines and accumulated observation across at least multiple human lifetimes. They were doing science without the word. And there's something specific to say about the word lost. People talk about lost ancient knowledge as though it was secret, as though it was deliberately hidden or erased. The truth is simpler and sadder. Knowledge requires infrastructure to survive. It requires the supply chains that brought pozzolana from Pozzuoli to the construction sites of North Africa. It requires the training pipelines that produced Inca stonecutters who could hold tolerances in fractions of a millimeter. It requires the institutional memory of the Stanford-affiliated archaeological research team, which had to be assembled from scratch and given years of fieldwork before they could begin to read what the Chavin builders had encoded in stone 3,000 years earlier. When Rome's Western Empire collapsed, the Pozzolana supply chain collapsed. When the Spanish invaded Peru in 1532 and killed or displaced the Inca master masons, the training pipeline for polygonal ashlar collapsed. The knowledge was not hidden, it was starved. It could not survive without the people who practiced it, the systems that sustained those people, and the demand that kept both alive. That is why modern engineers study these ruins, not as curiosities, but as competitive threats. Concrete that lasts 2,000 years against concrete that lasts 50 years is not a historical footnote. It is an engineering problem with a known solution that we have been unable to replicate at industrial scale for nearly a century since we rediscovered what the Romans were doing. And the last thing you need to hear about this is what happened in 2022 in Cusco, Peru, when researchers Carlos Benavente and his team completed their archaeoseismological survey of Inca stonework across the ancient capital. They photographed and measured thousands of displaced blocks, fractured corners, and shifted courses and walls across the city. They fed the data into statistical models. They found the orientation and direction of ground shaking from 2 major seismic events. One was already in historical records, one was not. An earthquake that struck Cusco during Inca times, powerful enough to shear and displace stone blocks across the city, powerful enough to bend walls in ways that today's researchers could measure and calculate, had never been recorded. The Spanish colonial historians who came after the Inca conquest in 1532 did not mention it. The Inca oral traditions, filtered through colonial transcription, did not preserve it, but the walls remembered. When the earthquake hit, the Inca stonework did what it was designed to do. The polygonal joints flexed, the walls bent without breaking, the buildings survived. The stones recorded the direction of shaking and the geometry of how they shifted. And then for 500 years, they waited, holding that data inside the mathematics of their own damage, until a team of researchers in 2022 came with cameras and measuring tools and statistical software and read what the stones had recorded. The walls were the archive. The earthquake was filed, an undocumented seismic event, preserved not in any text, but in the precise angle of displaced stone, in a building technique designed by a people who understood that the earth was going to move, who built for that movement before it happened, who encoded the record of it into the structure itself, who left for the people who came after them, 5 centuries later, with different tools and different questions, evidence of something that had been forgotten, preserved in the joints, silent since the 16th century. Read in 2022, Stone remembers.